this video is not a problem. Instead, what it is, in physics or in motion, we tend to have lots of cases where I have some particle, for example, that's around in space, and it has some velocities and it's rotating about something, and sometimes it's confusing to understand about position, motion, velocity, linear velocity, acceleration, rotational velocity about some centering point or acceleration. And so here's just some fundamental math and some calculus in trig and algebra to help us understand why lots of times in physics 101 we're going to have cases why we're often going to have things moving around at constant rotational velocity, so therefore constant tangent velocity and at a fixed radius, and why equations simplify so much, and how it could be more complex if I have, for example, the radial position changing, and I have not a constant rotational velocity but I have some acceleration, and what kind of things you might want to consider there. And again, this is partially simple because I'm just going to go two-dimensional. So we're just going to go planar motion. We're not going to worry about motion in and out of the board. So let's get started. So we have a point here, a particle. So there's my particle right there. And I have some coordinate system attached to some inertial reference frame, for example, the surface of the world, and it's not moving. And it's my xy coordinate system. Okay? And I'll define my position vector r is position from the center of my coordinate system to wherever that point is. So r is going to move around and go to that, from that point to there. That's my positional vector r. Okay, and then at any moment of time, I'm going to say the angle between my x-axis is theta to that positional vector r. And I'll have my unit vector I'll call I hat, my unit vector in the x direction, and j hat, my unit vector of length 1 in the y direction. And then I'll have a coordinate system, I'll define another coordinate system, and this one's going to could be a non-inertial coordinate system because I'm going to allow it to move, and I'm going to, wherever that point is from this same center point here, the direction to that particle at that moment, we'll call the unit vector in that direction called r hat, and then perpendicular to that we'll call that alpha hat. So there's my two defined coordinate systems, and now we're going to talk about how r hat, that unit vector of length 1, can be defined. So that's a non-inertial coordinate system. We'll talk about how that can be defined in terms of this inertial coordinate system I hat and j hat. So this is the simple trig from that. That's clear. And then for alpha hat, unit vector there, this is the coordinate system relating that to my I and j hat coordinate system. And then just to, we'll take a derivative here because they'll be useful in the future. We'll take the derivative of r hat with respect to theta. And so I can take, the I hat term, this is not, that's a fixed coordinate system, so there's no change there. The only change is the derivative of cosine of theta, which is minus sine of theta. Take the derivative of that's again a constant, and this is what I end up with. And here I'll do the same thing. I'll take the derivative of theta hat with respect to theta. Again, take the derivative terms here, I get this. And kind of interesting observation you can see from this solution, you can see that this term right here, the dr hat d theta, is that. These are one and the same. Okay? So this r hat change in that with respect to theta, well, that's, you'd expect that is theta. You can kind of envision that as well. And then again here, the d theta hat d theta, this term is minus r hat. So if this changes in theta, well, that has a minus r hat directionality to it. So that's not surprising. So these are really not surprising observations looking at that. So these are kind of these kind of things are something we're going to use now in defining. Now we're talking about so here position and velocity. So here's my definition of what position vector r is. So this is my unit vector r. It has a length, whatever the magnitude of r is, and it's in the r hat direction. So this is always true. That's my position vector for r. And so if I take a derivative of the position vector r with respect to time, so that's a velocity related term, so position versus time. So that's so I'll have the using the product rule. So that's the derivative of this term with respect to time times that term plus this term times the derivative of that term. So right there. And then I can just drop this down here, and then this term right here I can divide into, I can say dr hat dt, well that's d theta dt, dr hat dt. See, that would be, that's just another way of writing this out. Okay? And so now, again, carrying it through here, same thing, that's stays unchanged. Well, d theta dt, that's the term. Dr hat dt, we remember from up here, that's theta hat. So I can substitute that theta hat for there. D theta dt, so that means how theta is changing with time. So how theta is rotating about here, well that's omega, that's my so theta is in radians, omega radians per second. That's my rotational speed. So I can substitute it here. So here's my velocity. I have a term which is in the r hat direction. So that's just saying, well, what's the change in r hat, the length, the magnitude of that length versus time. And so so if this point is moving out to here, from there to there, and it has no theta term, it has some velocity, the change in r hat, the magnitude here versus r, and that's in the r hat direction. So that talks about all of the velocity terms in that direction. And then if it has a rotational term, well, that shows up here. So that's r, the magnitude of r, instantaneous, what that length is, times the rotational speed. And you can, yeah, again, we can see here that, so dr hat magnitude dt, that's velocity in the r hat, the velocity in the r direction, and r omega, so so moving this way, its length at that moment in time, and the radians per second, well, that's my velocity perpendicular to r, which is in the theta hat direction. So this is a term saying at any moment of time, this is my velocity components: the velocity in the r hat direction, the velocity in the theta hat direction. So velocity in itself is a useful thing. And now we'll talk about acceleration. And rather than going down to this term, we'll use this term right here. Acceleration of that particle point, well, that's just the second derivative of, that's the derivative of this velocity with respect to time. So I'll take the derivative here, and then I can take this term right here, and I'll take the derivative of that with respect to time. So d squared for r in this here, and then times this r hat, and then I can do the product rule again, the derivative of this term with respect to time, this term times the derivative of r hat with time. And here I have three terms that will be multiplied together, so I can take the derivative of this with respect to time times this times the derivative of this with respect to time, which is here, and this times derivative of theta hat with respect to time. So here's my second derivative with respect to time of r hat, are these terms right here. And then once again I can do this, so right here the same. I can take this term right here, dr hat dt. I can do the same thing I did right here, call that d theta dt, dr hat d theta. And that's going to be useful because I'll be able to use these terms again. Just keep dropping those terms down. I can do the same thing with this last term, my d theta dt, put it dt over d theta over t, d theta hat over d theta. And that's going to be useful again. So we can see that I have this dr hat dt, r hat d theta term. So theta hat. And then here I have a d theta hat dt, which is minus r hat. So here's this full equation for the second derivative of this position vector with respect to time. And then grouping like terms from this equation, we have some terms in terms of r hat, these two. So I can bring those over here, bring that there, bring all that over here. So there's my r hat terms. And then I have three terms in terms of theta, so I'll bring that term here. You can see these two terms are the same. I have this and that the same, so I have two of them, so that's a term right there. And then the d theta dt, so that's rotational radians, theta is radians, t time, so radians per time, so that's omega, rotational speed, and I have omega omega, so omega squared. So there's my r hat terms. And then here, the second derivative of theta with respect to time is either the derivative of the rotational speed with respect to time, which is rotational acceleration. So you can write it either one there, and then this term right here. Again, the omega is d theta dt. And, so yes, the alpha is the radial speed, radians per second squared, is the derivative of the radians per second over time. Now, special case, which is probably you're going to have almost every time. So this is the general. So this for a planar equation, if you want to worry about acceleration of that particle in the r direction, so pointing towards the center, this is the terms you need to consider. So you need to consider it has some. If it's changing in length, well, it has some acceleration in this pointing towards the center direction, just because it's changing, because it's accelerating in that direction. If it's not changing in length, that term goes to zero, and then I have this term here, which is our familiar term saying it's my minus r omega squared pointing towards the middle. And here I have a term which is related to, in this theta direction, if I'm not going constant velocity, is kind of how I'm accelerating going around. Okay, and then I have this term is related to the change in the radial length and the omega term. So often, many cases, almost every case you're going to start out, we're going to have constant length, and that makes this equation a lot simpler. So any derivatives with respect to r, with respect to time, are going to be zeros. So this term is going to be zero, and that's going to be zero. So this term drops away only if the magnitude of r is a constant. So I end up with this term, okay, which is kind of a familiar term. It's my minus my length, my radius, is a consumed constant magnitude at this point, times the rotational speed squared, and that's in the r hat direction. And then if I am not going constant rotational speed, so this term goes away if I have constant r, so that there's no that term goes to zero. So I'm just left with this. So whatever radius and whatever radial acceleration I'm going to have, well, that's in the theta hat direction. And then this term right here, another way to write it is the v squared in the rotational direction over r. So these are equivalent ways to write that term. So when something's rotating about, something's moving, and even if it's moving constant velocity, it's going to have an acceleration always to the middle. So this term is not going to go to zero. It only goes to zero if something's rotating. This term can only go to zero if I have no velocity, which means there's a static point, and then obviously I have no acceleration. So if something's moving about a circle, it's going to have acceleration towards the middle. That's what's saying. If r is changing, well, it's going to be more complicated. But if r is a fixed length, this could just mean that term. And then if it's moving, and then I have a term in the theta, it's parallel to the motion, only if this thing has some acceleration. So if it doesn't have acceleration and it's moving at some constant rotational speed, so 5 RPM or 5 radians per second or some value, if that's just some constant, well, then that becomes zero. Okay, then the only acceleration I have is my acceleration toward the center. Okay, so this is the current term. A lot of times you just see this, but you need to know what assumptions were made to get that. If I have constant rotational speed and I have constant radial position, radial length, so this is just circling around, well then I have only acceleration towards the center, and it's of these magnitudes. And it's pointed towards the center.